Moving on now to trigonometric ratios for reflex angles. We apply a very similar principle to the trigonometric ratios for obtuse angles, and we saw that in the last video. So just moving on now, and I've just drawn two triangles here, okay? So here's a triangle in quadrant 3, okay? So there's our theta, okay, measured from the negative x-axis, okay, down to OP, okay, so this radius OP. This is again a unit circle, which means that it's got a radius of 1, okay, and I'll just put the x-intercepts and the y-intercept there, so that's -1 there, okay. So this triangle here in quadrant 3, okay, so it has a radius of 1, but it's positive, okay. So the adjacent side is negative, okay, and also the opposite side is negative as well. Now, recall that when we measure an angle on a number plane, the angle is always measured from the positive x-axis. So if theta is the angle inside the triangle, okay, if theta is the angle inside the triangle, the angle measured, though, that we need to indicate is actually the angle measured from the positive x-axis. So we actually should measure it from here, like that. Okay. So this is in fact the angle 180 degrees plus theta. So plus this little theta, this actually gives us the angle measured from the positive x-axis, okay, anti-clockwise until it lands here at point P. Okay. Now, given that the adjacent side is negative and the opposite side is negative, hypotenuse is positive. I might just get rid of that positive 1, just make it positive, just a plus. Okay. What does that mean then for the trigonometric ratios? So that means then that sine of theta, okay, so that's 180. Actually, we mean the reflex theta. That's going to be opposite over hypotenuse. Okay, so opposites are negative over a positive. So sine is going to be negative in this quadrant. Okay, cos of theta is adjacent, which is negative over hypotenuse. So it's going to be negative over positive, and that's going to be a negative. And tan of theta, okay, is going to be opposite over adjacent. It's going to be negative over negative, and that's going to give us a positive. So tan is in fact positive in quadrant 3. And just to sort of maybe just to show you a quick example of that, if you looked at, for example, tan of, I don't know, let's say 45 degrees, we know that tan of 45 degrees is equal to +1. What about tan of 180 degrees plus 45 degrees? In other words, there's 45 degrees, okay, up this way. Swing it around another 180 degrees. So it's aiming here, so it's in quadrant 3. Okay, so that's 225 degrees. So that's equal to tan 225 degrees, and guess what? It equals 1. Okay, tan of 225 is equal to 1. Because it's just the same triangle as it is in quadrant 1, but we've just, again, we've flipped the triangle this way, and then we've flipped the triangle from above the x-axis to below the x-axis. But it's still the same triangle. They're still congruent to each other. So nothing's changed really. All that's changed is the angle that we measure. We're measuring it from, obviously, from the positive x-axis. But the only other thing that changes as well is whether the adjacent and the opposite sides are whether they're positive or negative. Okay, so in quadrant 1, all sides are positive. In quadrant 2, it was only the adjacent side that was negative. In quadrant 3, it was the adjacent side and the opposite side that are both negative. Okay, and so let's see then what happens when we flip this triangle from quadrant 3, flip it over to quadrant 4, okay, which is really the same as taking the triangle in quadrant 1 and flipping it over the x-axis or about the x-axis, so that for quadrant 1 it flips sort of in the vertical direction, so it lands here. Either way, it's the same thing. Okay, so what's going on here? Okay, again, hypotenuse is positive. This time around, the adjacent side, it's to the right of the origin, that's positive as well. But the opposite side is negative. It's below the x-axis. Okay, it's negative. So the theta that we're referring to here, and I'm going to use a different color here, so it's starting to get all, diagram's starting to get a little bit crowded. Okay, so there's our theta there, okay? And that's theta measured kind of backwards, isn't it? It's measured clockwise from the positive x-axis. But hang on, doesn't the rule book say, according to the right-hand rule, that angles should be measured anti-clockwise? Oh, well, we'll have to deal with that too, don't we? All right, so let's see what's going on in quadrant 4. All right, we know then that in order to get to quadrant 4, okay, we can go a full 360 degrees around and then take away theta. Okay, so this is theta is acute because theta is really the angle inside the triangle. So you know it's acute in a right angle triangle. But in order to locate it correctly in quadrant 4, okay, we need to basically spin this Q, this point Q. We need to basically turn it all the way around, do a full 360, and then come back. Theta. Okay, so in other words, we're going to look at the quadrant 4 angle is going to be determined by subtracting theta from 360, in other words. Okay, but before we go any further, let's have a look at the sine, cos, and tan ratios. So sine theta in this quadrant, okay, is opposite, okay, over hypotenuse. It's negative over positive, and that's going to give us a negative. Okay, cos of theta is equal to adjacent over hypotenuse, that's a plus over plus, and that's going to give us a positive, okay? And tan of theta is equal to opposite over adjacent, so that's going to be negative over positive, and that'll give us a negative. So it's cos of theta here in quadrant 4, cos of theta is positive. That's the all stations to central, the C refers to cosine. I'll summarize this in the next video, so just as a bit of a summary of this video and the previous video, just a quick kind of a quick run through all that, okay, and introducing it to all stations to central, of course. Okay, so as an example, okay, if we look at, say, for example, cos of 60 degrees, okay, cos of 60 degrees is equal to half, okay, we know this. Okay, if you want to try it for yourself, of course, remind yourself that's an exact ratio. Cos of 60 degrees is equal to half. But what about cos of 360 minus 60 degrees? Okay, so cos of 360 degrees all the way around, take back 60. So minus 60, right, is equal to, that's cos of 300 degrees, okay? And no surprises there. What do you think you're going to get? Positive half. System works, okay? So you get half because the adjacent side is positive and the hypotenuse is still positive. So in fact, the cosine doesn't even matter. And remember from the very beginning, in fact, in the last video, we looked at the coordinates x, y. X is a positive coordinate. In fact, it doesn't matter whether the triangle is above, okay? I might just sort of sketch it in there, right? If the triangle is above or below, isn't the x coordinate the same anyway? It happens to be the same adjacent side regardless. Okay, these two triangles have a common positive adjacent side. It's just the opposite sides go from positive to negative. Okay, so which means that sine goes from positive to negative. Okay, and that's why the sine of theta is used to represent the y, or the y coordinates represented by sine of theta. Okay, and cos of theta represents the x coordinate. Okay, so in the next video, we'll have a look at some examples, okay, and we'll summarize all of this, and we'll have a look at some examples of trigonometric ratios for basically any angle. The only other thing I haven't looked at though is negative angles. Okay, so for example, what about cosine of negative 60? In fact, while we're at it, why don't we just have a quick look at that? I'm not going to elaborate too much on it, okay, but I just thought while it just popped into mind there, what about, say, cos of negative 60 degrees? Or, for example, tan of, say, negative 45 degrees? Or, for example, sine of, say, let's say, minus 100 degrees. Okay, what's going on here? So let's have a look at the first one, cos of negative 60 degrees. Okay. Negative 60 means we're measuring backwards, we're measuring clockwise, in other words. There's the positive x-axis, which means we're coming back 60 degrees. okay? But we know that's incorrect. We can't measure an angle clockwise. We need to convert it into an angle that is anti-clockwise, or measured in an anti-clockwise direction. When I say it's incorrect, I don't mean it's necessarily wrong. Your calculator can still deal with that. That's fine. But we need to know how to interpret this negative 60. This negative 60 is the same as going back the other way, measuring it in the conventional sense. That's going to be 300 degrees. Okay, so 300 degrees going forwards is the same as 60 degrees going backwards. So really, this is just the same as cos of 300 degrees. In fact, if you add 360 to it, add 360, that's just going around just another full circle. Every 360 degrees means we're just going around in a full circle. Add another 360, you go around in a full circle. Same thing with tan of negative 45. Let's add 360 degrees to that. What do we get? Okay, we get 315 degrees. Okay, what about sine of 100, negative 100 degrees? Okay, sine of negative 100 looks like there's 90 going back 90 degrees. That'll probably be something like that there. Okay, so that's negative 100 degrees. What's that as an angle measured in the forward direction? Okay, in the clockwise direction. So this angle there, what would that be? Okay, in fact, if you add 360 to negative 100, okay, what do you get? You get 260 degrees. Okay, and again, if you don't believe me, try it. All right, this is why experimentation is great. In fact, you'll learn a lot in mathematics just by experimentation. Okay, there's a lot in common, in fact, between science, the subject of science, and the subject of mathematics. In fact, the best way to learn mathematics, or one of the best ways to learn, experiment, play. All right, sine of negative 100, negative 0.9848. Okay, what about sine of positive 260? Get the same value. Okay, it happens to be basically the same line. All right, so we can keep turning around and around and around and around. In fact, you can keep adding 360 to this. In fact, add 360 degrees. Guess what? You get the same value. Add another 360 degrees. You get the same value, and so on. Right? In fact, you can add 100 or 1,000 times 360 degrees. You get the same value. Doesn't even matter. You're just going around and around and around in circles. Hopefully you don't get too dizzy doing that though. But this is the beauty of it. This is, again, now you've learned, I guess, the connection between trigonometry and circles and circular measure, going around and around the circle, looking at the right angle triangle that's formed inside that circle. And you'll see that right angle triangle just keeps moving around, and it's just, and goes back to where it started again each and every time.